This conference will now be recorded.
Yeah. So, dear students, so in the last session, we have discussed about operations on random variables, right? And also, we have discussed about what is moment, and by using the moments, how do you find out the statistical parameters like statistical mean, statistical variance, and standard deviation, and also skew. Along with the skew, we have discussed about coefficient of skewness, right? So these are the statistical parameters that can be derived by finding the moments, right? So to find the moments, here we have discussed about Chebyshev inequality in the last class, and also we have started the moment generating functions, or the functions which can generate moments. And as we have discussed in the last session, there are two types of functions which can generate moments. And first one is characteristic function, right? And the second one is moment generating function. So in the last session, we have discussed about characteristic function. What is characteristic function? The characteristic function is nothing but the expectation of e power j omega x for any random variable x, right? So in the integration form, you can write it as integral minus infinity to plus infinity e power j omega x into fx of x dx. And that is the way to define the characteristic function. And also we have discussed that by using the characteristic function, how to derive the moments, or the moments about the origin are discussed in the last class, right? So that is, we have derived the formula for m suffix n by using the characteristic function, right? So now we are going to discuss about the properties of characteristic function. Why? Because while analyzing the characteristic function, or while deriving the moments by using the characteristic function, we should be in a position to understand the characteristic functions, right? So therefore we are going to discuss about properties of characteristic function, right? And the first property is, in the properties, the first property is pi x of 0 equal to 1. Pi x of 0, that is, at omega equal to 0, the characteristic function will be equal to 1, right? So you can also prove this property. So coming to the proof, you can take the proof like this. That is, the proof is pi x of 0 equal to, as we all know that the definition for the characteristic function is pi x of x equal to expectation of e power j omega x. When omega equal to 0, that exponential term becomes 0, right? The power term becomes 0. Therefore, expectation of e power 0. As a result, we will be getting this as expectation of 1. So therefore, expectation of 1 is a constant. Directly by using the property you can write, or by using the formula, we know that e of 1 equal to integral minus infinity to plus infinity 1 into fx of x dx, and always the total area under the density curve, as per the property of density function, it is absolutely equal to 1. Therefore finally pi x of 0 equal to 1. This is the way to prove the property, that is pi x of 0 equal to 1, right? Coming to the second property, the second property is pi x of minus omega equal to pi x of omega bar. That is, if omega is replaced by minus omega, then ultimately you can also take that particular pi x of minus omega as pi x of omega bar, right? So that is, how do you prove this? As pi x of omega is complex function, and I hope you're all aware of what is bar. If at all, if I take the bar for any complex function, if I take a plus j omega, a plus j omega bar becomes a minus j omega, e power plus j omega. The bar of e power plus j omega, that is e power plus j omega bar, is nothing but e power minus j omega. That is complex conjugate, right? So you can also prove this property. That is, we know that pi x of omega equal to expectation of e power j omega x. By using the Euler's relation, I am expanding that exponential term into the sinusoidal terms. Can I write like cos omega x plus j sin omega x? Yes. Therefore, I am writing it as expectation of cos omega x plus j sin omega x. So now I am taking pi x of omega bar. So since pi x of omega bar is nothing but complex conjugate, the term e power j omega x becomes e power minus j omega x. So therefore, the expectation of e power minus j omega x, which is equal to expectation of cos omega x minus j sin omega x, right? So here, if I take the same equation, if I represent in the other form, that is, if I take that minus into, that is, instead of omega, if I write minus omega, so ultimately here I should write here cos of minus omega into x. And anyway, for the cos theta equal to cos minus theta. Therefore, I am just the sign for cos is not changed here. But whereas in the case of sine, the sine minus omega is not equal to minus sine omega. It is not equal to sine omega. It is equal to minus sine omega. Therefore, the symbol in between the two terms has become plus, right? So therefore, here I can write this particular function as pi x of minus omega. Why? Because from the first definition, pi x of omega is cos omega x plus j sin omega x, expectation of cos omega x plus j sin omega x. Whereas in this case, I have in the place of omega, I have minus omega. Therefore, the particular function can be written as pi x of minus omega. Therefore, pi x of omega bar equal to pi x of minus omega. Hence proof. Right? This is the way to prove this particular property. Right? So coming to the third property. So I repeat, first property is what? Pi x of 0 equal to 1. Second property is pi x of minus omega equal to pi x of omega bar. Coming to the third property. So here, what is the third property? Pi ax of omega. If at all, if the random variable is multiplied by a constant a, then the characteristic function will be equal to pi x of a omega. So that is pi ax of omega equal to pi x of a omega. You can also prove this property. How do you prove? Pi ax of omega equal to, in the place of x, we have ax. So therefore, that expectation will become expectation of e power j omega into ax. Right? I'm just rearranging the terms, and the rearranging terms are now e power j into, after rearranging the terms will be e power j into a omega into x, right? So this is nothing but pi x of a omega. That is simple proof, right? So pi ax of omega equal to pi x of a omega. And coming to the fourth property, if at all, if the any two random variables are independent random variables, and then if I take the characteristic function of their sum, that is pi x plus y of omega, pi x plus y of omega equal to pi x of omega into pi y of omega. That is, their individual characteristic functions will be multiplied, right? So you can also prove this property. How do you prove? Pi x plus y of omega equal to, as per the definition, expectation of e power j omega into x plus y. In the integration form, I can also write it as integral minus infinity to plus infinity e power j omega into x plus y into fxy of x comma y into dx dy. Right? So what is this fxy of x comma y? So earlier we did not see any function which is in the form fxy of x comma y, and soon you are going to get much about this particular function. But now here you just remember the function as joint density function. That is, as the two random variables are involved here, we call the density function here as the joint density function. Fxy of x comma y is called joint density function, right? So x comma y are independent, and here one more thing you need to remember is, if at all, if any two random variables are independent or statistically independent, you can write the joint density function equal to the product of individual density functions. That is pi xy of x comma y equal to fxy of x comma y equal to fx of x into fy of y. We are going to prove this relation in the further topics. For time being, you just remember this relation, right? So fxy of x comma y equal to fx of x into fy of y, and when the two random variables x comma y are statistically independent, right? So by using this relation, if I substitute this, how can I write pi x plus y of omega? Pi x plus y of omega equal to integral minus infinity to plus infinity e power j omega x into e power j omega y into fx of x into fy of y into dx into dy. That is e power j omega x plus y is expanded here, and fxy of x comma y is substituted here. The relation for fxy of x comma y is substituted here. So therefore, I'm just separating this into two integrations. One is with respect to y, another one is with respect to x. So finally, if you observe here, the first one is nothing but the definition of one characteristic function, that is here definition for one characteristic function. The second one is definition for another characteristic function. Therefore, I can write it as pi x of omega into pi y of omega, right? So this is the proof we can take. And the last property of the characteristic function is expectation of e power j omega into ax plus b, which is equal to e power j omega into pi x of a omega. So it is a very simple proof you can take. Just thing is, you just expand that exponential term, right? So e power j omega into ax plus e power j omega into b. So already we have proved that the expectation of e power j omega ax is nothing but pi x of a omega. That is the third property. The only term left over here is e power j omega b. Since it is a constant with respect to x, you just keep it outside. Therefore, that particular relation will be e power j omega b into pi x of a omega, right? So total 5 properties we have discussed for characteristic function. The first property is pi x of 0 equal to 1. Second property is pi x of minus omega equal to pi x of omega bar. Third property is pi x of omega equal to pi x of a omega. Fourth property is pi x plus y of omega equal to pi x of omega into pi y of omega. And the fifth property is expectation of e power j omega into ax plus b is e power j omega b into pi x of a omega. Right? So you need to remember the 5 properties along with the proofs. And let us take a simple problem here. So already we have discussed in the last class, that is always the characteristic function will be maximum at omega equal to 0 and the value is absolutely equal to 1. That is mod pi x of omega is always less than or equal to pi x of 0. That is the statement given in the last session. So let us prove this, and sometimes we can also expect this relation in the form of a problem in the examinations, right? So let us take here the problem. For any random variable x, prove that mod pi x of omega less than or equal to pi x of 0, which is equal to 1, right? How do you prove this? Yes, we know the formula for pi x of omega. First you write the formula. What is pi x of omega? Expectation of e power j omega x, or integral minus infinity to plus infinity e power j omega x into fx of x dx, and take the mod, right? So now I'm just taking the mod into the integration. So I can write it as integral minus infinity to plus infinity mod j omega x into fx of x dx, right? So finally here, how can I write this one? Since I'm taking this particular product term into the individual terms, the mod is separated here. Therefore, always this original function magnitude or mod will be less than this particular mod j omega x into mod fx of x. We know this particular inequality in the mathematics, right? So therefore here I can write the relation as mod pi x of omega less than or equal to integral minus infinity to plus infinity mod e power j omega x into mod fx of x dx. Anybody, what is mod e power j omega x? Mod e power j omega x in the sense e power j omega x can be written in the form of sinusoidal terms, right? As per the Euler's relation, e power j omega x equal to cos omega x plus j sin omega x. If I, that is, it is in the form a plus jb. So if it is in the form a plus jb, if I find the magnitude of a plus jb, how do you write? Mod a plus jb equal to under root a square plus b square. Am I right? Similarly, mod cos omega x plus j sin omega x equal to what? Under root cos square omega x plus sin square omega x. We all know that cos square theta plus sin square theta equal to 1. Therefore, finally, what is the mod value for mod e power j omega x? Absolutely equal to 1. So therefore, here mod pi x of omega is less than or equal to integral minus infinity to plus infinity fx of x dx. So already we have discussed this as a first property. What is that? Pi x of 0 equal to integral minus infinity to plus infinity fx of x dx, or the total area under the density curve is equal to 1. Therefore, I can write it as mod pi x of omega is less than or equal to 1, right? So this is the way to solve the problem. It's a very, very important problem. You just remember this. Now, let us move on to the next function which can generate the moments. The first one is characteristic function, and the second one is moment generating function, right? So what is moment generating function? Let us see. In the short form, we can also call it as MGF, right? So MGF, moment generating function of a random variable x, is defined by, how do you define? See here, mx of v, right? So the notation for moment generating function is mx of v, whereas the characteristic function is represented by pi x of omega. And just remember the variable here, and there we have used the variable omega, but in this moment generating function we have used the variable v, right? And in some literature it is also given like mx of t, the variable taken as t in some literature. Don't be confused, it may be mx of v or mx of t. So the formula for this is, you can write the MGF as mx of v equal to expectation of e power v into x, e power vx. So in the integration form you can write integral minus infinity to plus infinity e power vx into fx of x dx, right? So here, what is v? V is a real number same as your omega, and it is varying from minus infinity to plus infinity. Now we can write, so what is the purpose of moment generating function or characteristic function? Ultimately to derive the moments, right? To derive the moments. Why? Because the moments are used for finding the statistical parameters. That is our ultimate goal. So therefore we need to write the expression for nth moment by using this MGF, right? So the nth moment about the origin of the random variable x can be computed using, what is the relation here? M suffix n equal to nth differentiation d power n by dv power n mx of v when v equal to 0, right? V equal to 0. If v, that is, we need to substitute v equal to 0 after finding the differentiation, right? So by using this I can generate the nth moment. If I need to find the first moment, I have to substitute n equal to 1, or to find the moment, second moment, I need to substitute n equal to 2. Like that I can derive the moments using the moment generating function. You can prove this relation. Why? Because we are given with the formula for mx of v in terms of expectation, right? So we can also derive this relation. Sometimes in the exams also you'll be given, and I will be asked to derive this particular relation. So let us see how to derive. Proof. Mx of v is given as integral minus infinity to plus infinity e power vx into fx of x dx, right? So now we'll do one thing. Apply the differentiation with respect to v on both sides. So if I apply the differentiation, what happens? The left hand side will be d by dv of mx of v. The right hand side will be d by dv of integral minus infinity to plus infinity e power vx into fx of x dx. So here, if I take the differentiation into the integration, it becomes integral minus infinity to plus infinity. I'm just changing the order of integration and differentiation. So here it becomes d by dv of e power vx, and ultimately fx of x is independent of v. Therefore, it is coming out of the differentiation d by dv of e power vx into fx of x dx, right? So now you can find out the differentiation of e power vx. What is the differentiation of e power vx? Integral minus infinity to plus infinity e power vx into x. That is, e power vx into x is the differentiation of this particular d by dv of e power vx. So the next term is fx of x into dx. So now I'm taking v equal to 0 on both sides. So if I apply v equal to 0, d by dv of mx of v, if v equal to 0, this will be equal to integral minus infinity to plus infinity. Earlier we had e power minus vx, sorry, e power plus vx. So here when v equal to 0, e power 0, the term will be equal to 1. 1 into x into fx of x dx, right? So here you know what is x into fx of x, integral minus infinity to plus infinity x into fx of x dx, nothing but expectation of x. In fact, expectation of x is nothing but the first moment about the origin or the mean value. So therefore m1 equal to e of x equal to integral minus infinity to plus infinity x into fx of x dx is nothing but d by dv d by dv mxv for v equal to 0. Am I clear? Similarly, you can find m2. M2 in the sense, m2 is nothing but expectation of x square. That is second order moment about the origin, or you can also call it as what? Mean square value, right? In the last session we have discussed mean square value of the random variable, so which is equal to integral minus infinity to plus infinity x square into fx of x dx, which can be derived by using the moment generating function like this: d square by dv square mx of v when v equal to 0. And similarly the general term also can be taken, that is the nth moment can be derived by using the moment generating function, right? That is mn equal to d power n by dv power n mx of v when v equal to 0, right? Clear? So this is the way to derive the moments by using the mgf, moment generating function. Coming to the properties, we do have the properties for mgf same as your characteristic function, and almost all the properties are similar to the properties of characteristic function, right? So let us see here. The first property is max of v equal to mx of av. The same property we have seen as the third property in the characteristic function. Same way the proof is also similar to the proof in the characteristic functions, property of characteristic function. So let us see the proof here. What is the proof? So here max of v is nothing but expectation of e power v into ax, right? So now let us change the order here. That is, if I rearrange the terms, expectation of e power av into x, right? So therefore I can write it as mx of av. Simple proof, right? Coming to the second property of mgf, what is the second property? Mx plus a of v equal to e power av into mx of v, right? So here we can prove this. How do you prove? That is mx plus a of v, in the place of x we got x plus a, so therefore the term will become expectation of e power v into x plus a, right? So therefore I can just write it as e power expectation of e power vx into e power a into v. If I take that e power av outside, how can I write e power av into expectation of e power vx? What is that expectation of e power vx? Nothing but mx of v. Therefore e power av into mx of v. That is the second property of the mgf. Third property is what? Mx plus a by b. That is, if the random variable is even, divided by constant. You can write the moment generating function as e power av by b into mx of v by b. It is also very easy to prove. That is, in the place of x, we got x plus a by b, right? So expectation of e power x plus a by b. So now it is nothing but expectation of e power v into x by b into e power v into a by b, right? So here, if I take that e power v into a by b outside the expectation, as it is independent of x, so ultimately that expectation becomes e of e power v into x by b, right? So therefore, I can also write it as e power v into a by b into expectation of x into v by b, just rearranging the terms. So now, how can I write this one? E power av by b into mx of v by b. So first property is max of v equal to mx of av. Second property is mx plus a of v equal to e power av into mx of v. Third property is mx plus a by b of v equal to e power av by b into mx of v by b, right? And we do have the fourth property. The fourth property is mx plus y of v equal to mx of v into my of v. If at all, if x comma y are independent random variables, right? Similar to your previous characteristic function, right? That is mx plus y of v equal to expectation of e power v into x plus y. And here also we get the joint density function, that is fxy of x comma y dx dy. We all know that the joint density function equal to the product of individual density functions, if at all, if x and y are independent random variables, right? So therefore, if I substitute it, how do you write? Mx plus y of v equal to integral minus infinity to plus infinity e power vx into e power v by, I'm just expanding the exponential here, right, into fx of x into fy of y dx dy, right? So therefore, if I write separate integrals, and the resultants can be written as mx of v into my of v. Am I clear? Simple way to derive the relation. So let us take a problem related to moment generating function, right? Simple problem. Answer also given. Just have a look. We need to do next problem. Have a look. Just read the problem carefully. A loss for the company has a moment generating function mgf m of t equal to 0.16 by 0.16 minus t when t is less than 0.16, right? So what is the given data here? Loss for a company has moment generating function. That is moment generating function of what? Loss for a company. That is loss, moment generating function of loss is given. An insurance policy pays a benefit equal to 70% of the loss. 70% of the loss. What is the benefit? Benefit is equal to 70% of the loss. What is the moment generating function of the benefit? Right? What is the moment generating function of the benefit? So what is benefit actually? If I represent x as loss, y as benefit, what is the relation between loss and benefit? Loss is x, benefit is y. Y is equal to 70% of x. Can I say 0.7 into x? Yeah. So what are you supposed to find? Moment generating function of benefit. That is moment generating function of random variable y. That is my of t. My of t is nothing but expectation of e power ty. But we don't know this. So we know only expectation of e power what? X. That is e power xt or tx. Right? So therefore, expectation of e power t into what is y? Nothing but 0.7x, which is equal to mx of 0.7 into t. If I substitute this in the given data, I can write it as e 0.16 by 0.16 minus 0.7t. Understood how to solve the problem? So let us take one more problem. Simple problem. A company insures, again the same type of problem. A company insures homes in 3 cities. So what are the three cities? J, K, L, right? Let us say J for Jaipur, K for Kolkata, and L for Lucknow. Jaipur, Kolkata, Lucknow, right? In three cities, right? In three cities, the company is insuring the homes. The losses occurring in the three cities are independent. Why? Because Jaipur is in Rajasthan, Kolkata in West Bengal, and Lucknow in Uttar Pradesh. And the three cities, in the three cities, the losses occurring is independent. Independent. The moment generating functions for the loss distributions of the cities are moment generating functions are given for the three cities. What are the moment generating functions given for the Jaipur? Mj of t equal to 1 minus 2t power minus 3 whole power minus 3. Mk of t equal to 1 minus 2t whole power minus 2.5. Ml of t equal to 1 minus 2t whole power minus 4.5. This is the given data. Three moment generating functions for three cities is given. Let X represent the combined losses from the three cities. Combined losses in the sense X equal to, if I take the loss for Jaipur, let us say J, loss for Kolkata, let us say K, loss for Lucknow, let us say L. So can I say the loss, total loss, combined loss, X equal to J plus K plus L. If I say like that, so here what are you supposed to find? If that particular X is representing the combined loss of the three cities, calculate expectation of X cube. Expectation of X cube, right? Just pause the video and try to solve. So let us see the solution now. Right. So what is X? Combined loss. First, what is the given data? The moment generating functions of three cities is given, right? So you are supposed to find what first? The moment generating function of X, combined loss. After that, by using that, you can derive the, ultimately you can derive the moments. That may be expectation of X or expectation of X square or expectation of X cube. Why? Because we have the relation for finding the moments using the moment generating function. Correct? Right? So what are you supposed to find? E of X cube. To find E of X cube, first we need to find the moment generating function of X. How do you find? First, let JKL denote the losses from the three cities. Then X equal to J plus K plus L. Yes, exactly. Since JKL are independent, the moment generating function for their sum X is equal to the product of the individual moment generating functions. Which property it is? It is the last property of MGF, the fourth property, mxy plus y of v equal to mx of v into my of v. But here in this case, three random variables are involved. Therefore, mj of v into or mj of t into mk of t into ml of t. Right? So therefore, so how do you write the mx of t? Mx of t equal to mk of t, mj of t into ml of t. So finally, I'm going to get the moment generating function as 1 minus 2t power minus 10. Yes, we got moment generating function. So what are you supposed to find actually? Expectation of X cube. How do you find? We have the relation. What is that relation? The moment generating from between moments and moment generating function. That is the differentiation of moment generating function, and after the differentiation you need to apply or substitute v equal to 0. That is d by dv of mx of v, mx of v when v equal to 0 will be the first moment of the random variable x, right? Similarly, nth moment, already we have the relation d power d and d power n by dv power n of mx of v when v equal to 0 becomes nth moment. But we need what? Third moment. So let us see differentiation. If I differentiate once, it becomes m dash of t. It becomes in fact e of x minus 2 into minus 10 into 1 minus 2t power minus 11. And again, if I differentiate, it becomes e of x square. That is second derivative, m double dash t. But I need what? Third derivative. Why? Because e of x cube is the required one here. So m triple dash of t equal to minus 2 whole cube minus 10 minus 11 minus 12 into 1 minus 2t power minus 13. So simple differentiation here, right? And no rocket science is involved, just simple differentiation, right? So therefore expectation of x cube is what? Mx triple dash of 0. You need to substitute t equal to 0 here. So therefore minus 2 whole cube minus 10 minus 11 minus 12, the total product will be equal to 10,560. That is the third moment of the random variable x is 10,560, right? So this is the way to solve the problem, easiest way, right? Understood the problem? Fine. And next, let us move on to the next topic. So far in this session, we have discussed characteristic function, properties of characteristic function, moment generating function, and how to derive the moments using the moment generating function, and the properties of moment generating function, and applications or problems related to moment generating function, right? And let us move on to a new topic, transformation of a random variable. In the name itself, transformation in the sense we are just transforming random variable, one random variable into the other random variable. Transform in the sense change. Why do you require actually? First, the motivation behind the transformation of a random variable is basically here one example is given here. Let us take the illustration here. What is the motivation required? Motivation behind the transformation actually. Consider a situation in the real time where the velocity of a particle is distributed according to the random variable v. Velocity is considered as random variable v. Based on a particular realization of the velocity, there will be corresponding value of kinetic energy E. Based on the particular realization of the velocity, there will be a corresponding value of kinetic energy E. And we are interested in the distribution of kinetic energy. Why? Because here distribution is actually the distribution is based on the velocity, but we are interested in the distribution of kinetic energy. So ultimately, do we need to transform the random variable v to the random variable e or not? Is it right or not? Why? Because the distribution is given for velocity, but we need the distribution for kinetic energy. Therefore, I need the transformation there from v to e, right? But how do you apply the transformation? Ultimately, to apply the transformation, we need to know the relation between these two. What is velocity? What is the relation between velocity and kinetic energy? If you don't know the relation, you cannot transform, right? So to transform variable v to variable e, you need to know the relation between the two. If you know the relation, you can transform, right? So based on the relation, you can decide which type of transformation is required, right? So clearly, this is the scenario where we are asking for the distribution of a new random variable, which depends upon the original random variable. New random variable here in the case is, in this scenario, is E. Already existing random variable or original random variable is V. And through a transformation, such situation occur often in practical applications. Not only this, in most of the cases, we'll be getting this type of transformation, right? Now, how do you take the transformation? In the real-time applications, quite often, one may wish to transform one random variable x to new random variable y. Usually, this is done by means of the transformation. Y equal to transformation of x. We represent like this. Y equal to t of x. That is, I'm transforming x to y. I'm just here a black box here. That black box is nothing but y equal to relation between x and y. Y equal to t of x. Y equal to T of X. It is the relation. Now, this transform is general, can be linear or non-linear or staircase or segmented. The relation between X and Y may be linear or maybe non-linear, maybe staircase, any relation may be segmented. We cannot give assurance only this particular relation should be there. And similarly, X can be continuous, discrete or mixed. Any type of random variable based on the application. And every time you cannot expect only discrete random variable or continuous random variable from the experiment, right? So let us take different types of transformations. So here, how many types of transformations you have? Monotonic and non-monotonic transformations. Again, in the monotonic transformation for continuous random variable, monotonic transformation for discrete random variable, non-monotonic transformation for continuous random variable, non-monotonic transformation for discrete random variable. So if at all, if I have the continuous random variable, how do you apply the transformation? And what do you mean by monotonic? What do you mean by non-monotonic? And how do you decide whether the transformation is monotonic or non-monotonic? Ultimately depends on the relation between the new random variable and the existing or original random variable. So in the previous case, the new random variable is kinetic energy E. The existing or original random variable is V, right? So therefore here, first one, let us take monotonically increasing transformation. Again, in the monotonic, we have increasing and decreasing, right? Again, we have monotonically increasing and decreasing. So now let us take monotonically increasing transformation of continuous random variable. So how do you transform? How do you transform the random variable? Let me take X random variable is transformed into Y. So how do you transform from X to Y? If the transformation is, if the relation between X and Y is monotonical relation. So in the sense what? A transformation T is a continuous random variable, a continuous random variable X is said to be monotonically increasing if it satisfies the condition. When you can say the transformation as monotonic transformation, if at all if T of x1, the transformation of x1 is less than transformation of x2. For any x1 less than x2, which are nothing but elements of the random variable x. For example, I have the random variable x. In the random variable, I have the elements. Transforming x to y in the sense nothing but transforming the elements of the random variable x into the elements of the random variable y. So that is, each and every element must be transformed. The transformation must be applied to each and every element of the random variable. If I consider two elements x1 and x2, so if the transformation of x1 is less than transformation of x2, when if the two elements are related like x1 less than x2, then that transformation is called monotonic transformation. Just see here, let y has a particular value y0 corresponding to the particular value x0 of x. y0 is element in the new random variable. x0 is element in the existing random variable. That existing random variable must be transformed to new random variable, or element x0 must be transformed to y0. So how do you take the relation? The two numbers are related by y0 equal to t of x0 or x0 equal to t inverse of y0. That is the relation. That is the relation. y0 equal to t of x0 or x0 equal to t inverse of y0. Or I can say like this, monotonically increasing transformation can also be represented like this. That is, the transformation or the relation between y and x, I can say, that is the better understanding you can take like this. The relation between y and x is increasing function. Increasing function. Relation between y and x is increasing function. So if x increases, y increases. If x increases, y increases. That is simply I can say, if I say y equal to 2x, what happens? if x increases, y increases. Am I clear? Right. Next, now the probability of the event y less than or equal to y naught. So it is y less than or equal to y naught must be equal to the probability of the event x less than or equal to x naught, because of one-to-one correspondence between the random variables x and y. So what I'm doing here, transforming in the sense, whatever the probability I have, that is probability of x less than or equal to x naught is transformed to probability of y less than or equal to y naught, right? That is called one-to-one correspondence. In the place of x naught, if I have x1, probability of x less than or equal to x1 must be transformed to probability of x less than or equal to y less than or equal to y1. Similarly, probability of x less than or equal to x2 must be transformed to probability of y less than or equal to y2. That is called one-to-one correspondence, right? So that is probability of y less than or equal to y not equal to probability of x less than or equal to x naught. That is called transforming the random variable x to new random variable y. Understood? That is, the relation is between x and y is increasing function, monotonically increasing function. For the definition of probability distribution function for this monotonically increasing, so what do you mean by this? That is, I have the random variable x, I am transforming to y. So for the new random variable, do I need to find the distribution function or not? Yes, I need to find. So how do you find? From the definition of the probability distribution function, the above equation can be written like this. That is, fi of y naught equal to fs of x naught or fx of t inverse of y naught. Right? Fi of y naught, that is the distribution function value of the new random variable at y naught is equal to fx of x naught. That is the distribution function value of x at x equal to x naught, right? From the properties of density function, if the above relation is valid, how do you write? If I apply the density function property, integral minus infinity to y naught, fi of y naught is nothing but integral minus infinity to y naught, fi of y dy equal to integral minus infinity to x naught, fx of x dx. Or in other words, I can also write integral minus infinity to t inverse of y naught, fx of x dx, right? So therefore, I can also derive the relation between new density function and the existing density function by using the Leibniz rule. You are aware of the Leibniz rule in the mathematics. So from the mathematics, if I take the Leibniz rule, here I can write this as the resultant of this particular integration as fy of y naught equal to fx of x naught into dx naught by dy naught. Dx naught by dy naught. Why? Because fi of y naught into dy naught equal to fx of x naught into dx naught. That is the Leibniz rule. I repeat, fy of y naught into dy naught equal to fx of x naught into dx naught. That is Leibniz rule. I am taking the differential term dy naught into the RHS. So therefore, fi of y naught equal to fx of x naught into dx naught by dy naught. Or I can also write x naught can be written as t inverse of y naught. Fx of t inverse of y naught into d t inverse of y naught by dy naught. Am I clear? That is, it is nothing but the new density function of the random variable, new random variable y at y naught. By using what? The existing density function at x naught, which is multiplied by some term. The term is dx naught by dy naught. Or not only, it is not only applicable for x naught, it may be x1 or it may be x2 or x3. Generally, I can write the expression like this: fy of y equal to fx of t inverse of y into dt inverse of y by dy. Or in the place of t inverse of y, simply I can write x, fy of y equal to fx of x into dx by dy. That is monotonically increasing transformation. If at all, if the transformation is monotonically increasing transformation between the random variables, the new different new density function or new distribution function can be derived by knowing or by taking the existing distribution function and density function using these relations, right? So in the next session, we are going to take monotonically decreasing transformation, right? We'll continue in the next session. Thank you.